this video, we're going to talk about the multiplication principle for counting. So we'll start with an example. If we roll a six-sided die and toss a coin, how many possible outcomes are there? And outcomes could be like a 2 and a tail, or a 5 and a head, etc. One way we could think about this is with a tree, with the different steps of our process in the branches of the tree. So first we roll a die, and the possible outcomes are 1, 2, 3, 4, 5, 6. Next, we're tossing a coin, and for each of those original outcomes, there are two possibilities for the subsequent toss of the coin. We could get a heads and a tail, we could get heads or a tail, we could get a heads or a tail, and so on. Now let's look at each of these sort of full branches of the tree and notice that each of these is a potential outcome. So here, this is 1 and heads, and that's one possible outcome. Here, for example, this is 4 and tails, and that's another possible outcome. So how many outcomes are there in total? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 possible outcomes here. So let's notice that this is equivalent to the number of lists of length 2, where the first entry is from 1, 2, 3, 4, 5, 6, and the second entry is from heads and tails. So, we've got these entries 2T, 5H, etc., and each of these branches of the tree corresponds with one of these lists of length 2. Something we can notice at this point is if we think about these possible outcomes as being elements of a list, where the first entry has 6 possible outcomes, the numbers 1, 2, 3, 4, 5, and 6, and the second entry has 2 possible outcomes, then how many possible outcomes were there for the entire list? There were 6 times 2 equals 12 possible outcomes for the entire experiment or the entire list of length 2. We are going to see this as a general rule, the multiplication principle for counting, that when we think about something with, step 1 and step 2, the number of outcomes for step 1 times the number of outcomes for step 2 is going to be the total number of outcomes possible for the entire experiment. So we'll state this a little more formally in a bit, but let's look at a couple examples on the way. So here, let's suppose that we have a list of length 3 made from the letters A, B, C, and D. So I'd like you to just pause for a moment and think about the number of possible lists there could be of length 3 from this set. Okay, so we could think of this as, our list of length 3 and how many possible values are there for the first entry. There are 4 possible outcomes that the first entry could have. We could have A, B, C, or D. Then we have a second step where we again have 4 possible outcomes for our next step. So whatever is chosen in the previous step, we now have an additional 4 outcomes from that. So this is going to be multiplication. And for the last step, again, we have 4 possible outcomes there as well. So 4 possible outcomes for this, and times 4 possible outcomes for this, and 4 possible outcomes for this. If you made this entire big tree, you would see that it has 4 to the third, 4 times 4 is 16, times another 4 is 64 possible outcomes. So there are 64 lists of this length that can be made from those 4 letters. Let's think about just a slightly different question. How many lists of length 3 can be made from these same letters where the letters cannot be repeated? So up here, like A, C was possible. Down here, A, C is not possible because A is repeated. So think about how many lists of length 3 can be made with this requirement. Okay, so we've still got, our first entry in the list, and there's 4 possible outcomes for that first entry. But then one of them has been used, so now we only have 3 possible outcomes for the second one. Like if this was B, then only A, C, and D are possibilities. And now we've used 2 letters, so there's only 2 letters left for that last entry of the list. So the total number of possible lists of length 3 with this restriction, where there are no repetitions, is 4 times 3 times 2, 12 times 2. There's 24 possible lists of length 3 from this set of 4 letters where no letters can be repeated in the list. So here is the more general multiplication principle. If a list of length n has A1 possible entries for the first element, A2 possible entries for the second element, etc., up to A sub n possible entries for the last element, then the number of possible lists of this type is A1 times A2 times ... times AN. So this is multiplication. Sometimes this is also stated in terms of steps. So if a procedure or an experiment has n steps, and step 1 can happen in A1 possible ways, step 2 can happen in A2 possible ways, etc., the number of ways the entire procedure can take place is A1 times A2 times A3 ... times AN. Note, like in the example above with no repetition, we must take into account situations where one entry affects the number of choices for subsequent entries. So this can happen, in different ways. One of the ways that this can happen is if we're talking about a list with no repeated elements. So let's just look at a couple more examples. So say we've got a door code that's a sequence of 4 numbers with the digits 0 through 9. How many door codes are possible? As another example, if there are 3 cards drawn one at a time and without replacement from a deck of 52 cards, how many possible sequences of card draws are there? So, one card draw could be Queen of Hearts, Jack of Diamonds, and 9 of, let's say Hearts again, would be a 3-card sequence of draws. So pause and try this out, and we'll talk about it together. Okay, so we've got a sequence of 4 numbers, 0 through 9. How many door codes are possible? Here, repeats would be allowed, right? Or, as long as we don't specifically say that repeats are not allowed, I could make my door code 1, 1, 1, 1, and that would be a bad idea. It would be very easy to hack, but I could do it. That would be a door code. Also note, if the door code was truly 2, 3, 5, 7, and you typed in 5, 3, 2, 7, that door would not let you in. The order of these elements matters. So these are lists of length 4 with repeats allowed. And there are, in our list of length 4, there are 10 choices, 0 through 9 for the first entry, 10 choices for the second, 10 choices for the third, and 10 choices for the fourth. So this is 10 times 10 times 10, or 10 to the fourth, which is 10,000. So that is the number of different door codes we'd have in this case. Next, 3 cards are drawn, one at a time without replacement from a 52-card deck. How many possible sequences of draws are there? One thing to note is, in general, sequence denotes order. So if there's an ordered sequence, if there's a sequence that says, the first thing is first, the second thing is second, that the order does matter. So order matters in a sequence. So we're drawing 3 cards one at a time without replacement. That means that there's no repeats. So because the card isn't replaced after it's drawn, we can't draw the Jack of Diamonds twice. So we've got 52 choices for our first element of the list. We've got 51 choices for our second, because we have drawn one of them out already, and 50 choices left for our third. So the total number of sequences of card draws here is 52 times 51 times 50. And we could also calculate that out. And that would give us 132,600. So let's do 2 more examples. First, suppose license plates in a particular state have 2 letters followed by 3 numbers. How many different license plates are possible under these rules? And second, how many lists of length 3 can be made from the letters A, B, C, D, E under the following conditions? So first, if the letters cannot be repeated. Second, if the letters can be repeated, then the letters cannot be repeated. Then repetition is not allowed, and the last letter must be A. Then repetition is not allowed, and the last letter must be a consonant. So try those problems out, and we'll talk about them together in a moment. Okay, so now we've got this basically list of length 5, where the first is a letter, so there's 26 possibilities for that. There's no rule that the letters or the elements can't be repeated, so we still have 26 possibilities for the second element. Now the third entry is a number with digits 0 through 9, so there's 10 possibilities for it. Now we've got another digit 0 through 9, so there's 10 possibilities for it. And lastly, another number 0 through 9. So the total possible number of license plates then is 26 times 26 times 10 times 10 times 10, or 26 squared times 10 to the third, and simplifying gives us 676,000. Next, if our letters can be repeated, then this is just a list where there are 5 possibilities for the first entry, 5 for the second, and 5 for the third. So there's 5 to the third, or 125 different possible lists of this type. If the letters cannot be repeated, then after we've chosen our first letter, we only have 4 possibilities for the second and 3 for the third. So this is 5 times 4 times 3, or 60. If repetition is not allowed and the last letter is A, so that means we only have 1 possible element for that last letter. What are now the possibilities for the first letter? Well, I've already used A, so there's 4 possible letters left that I could use. And now I've used A and 1 other letter, so there's 3 other letters that still can be used. So I've got 4 times 3 times 1 is 12 possible lists of this type. And lastly, repetition is not allowed, and the last letter is a consonant. So looking back up at my letters, my consonants are the things that are not vowels, B, C, and D. So I have 3 possibilities for what the last entry can be. Now, whatever I used 1 letter so far. So for my first entry, I now have 4 possibilities for it, anything other than what I've already used. And for my middle entry, I have now 3 possibilities here. I've used 1 letter here and 1 letter here. I have 3 left. So altogether, there's 4 times 3 times 3, 12 times 3 is 36 possible lists of this type.